James Webb Telescope, unexpected new discovery will shock you. Space exploration just got an upgrade with NASA's James Webb Space Telescope, or JWST for short, because it recently was able to show off its unparalleled ability to study the atmosphere of a massive exoplanet more than 1,100 light years away, realizing a great dream for astronomers. With the combined power of 18 individual mirrors working in perfect harmony to make up a single 270 square foot mirror, the JWST found signs of clouds, haze, and water signatures that were previously believed to not exist on this large, distant gas giant. Webb's near-infrared imager and slitless spectrograph were used to create the transmission spectrum of the hot gas giant WASP-96b, which provides only a little insight into the mission's exciting future of exoplanet study. Stick around to the end of this episode and explore with us the astonishing, unexpected finding made by the James Webb Space Telescope that has shocked the whole space industry. This discovery will most likely shock you as well. A far-off exoplanet's hot atmosphere is revealed by JWST. The hot, puffy gas giant planet that orbits a far-off sun-like star bears a telltale signal of water in its atmosphere, as seen by the James Webb Space Telescope. It also discovered indications of clouds and haze. The observation, which is the most in-depth to date, exemplifies the JWST's amazing capacity to study atmospheres hundreds of light years away. Based on minute reductions in the brightness of various hues of light, this observation indicates the existence of specific gas molecules. The Hubble Space Telescope has studied several exoplanet atmospheres over the last 20 years, detecting water for the first time in 2013. Nonetheless, Webb's instantaneous and more thorough study represents a significant advancement in the effort to define possible habitable worlds beyond Earth. WASP-96b, one of the Milky Way's more than 5,000 known exoplanets, is situated around 1,150 light-years away in the constellation Phoenix in the southern hemisphere. With a mass less than half that of Jupiter and a diameter 1.2 times larger, it represents a form of gas giant for which there is no direct counterpart in our solar system. WASP-96b is substantially hotter and puffier than any planet circling our Sun, with a surface temperature of more than 1,350 degrees Fahrenheit or 725 degrees Celsius. WASP-96b completes one cycle every 3.5 Earth days, orbiting incredibly close to its Sun-like star, just 1/9 the distance between Mercury and our Sun. WASP-96b is the perfect target for atmospheric investigations because of its massive size, quick orbital period, puffy atmosphere, and absence of polluting light from surrounding celestial objects. The WASP-96 system was seen by Webb's near-infrared imager and slitless spectrograph on June 21st for 6.4 hours while the planet traveled across the star. As a result, a light curve demonstrating the overall starlight dimming during the transit and a transmission spectrum showed that the brightness variation of individual infrared light wavelengths between 0.6 and 2.8 microns are produced. The light curve also confirms the existence, size, and orbit of the planet, which had already been established from earlier observations. The transmission spectrum reveals previously unobserved aspects of the atmosphere. The clear signature of water hints at haze, and provides evidence for clouds that were previously believed to not exist. The starlight that is filtered by a planet's atmosphere as it passes in front of the star is compared to the unfiltered starlight that is observed when the planet is next to the star to create a transmission spectrum. Because of the gas and dust in deep space, the JWST uses the infrared spectrum, which measures heat rather than light. It would be impossible for Hubble to see objects that are 13.6 billion light-years away. However, That spectrum is easily penetrated by infrared light. Because stray heat would distort Webb's infrared optics, just as stray light would distort Hubble's visible spectrum, Webb needs to be protected from stray heat. It must stay extremely cold for the telescope to work. This leads to some intriguing design elements incorporated by NASA, including a 5-layer heat shield the size of a tennis court that will block the sun, keeping the equipment free from the heat and radiation. In addition, putting the mirror in a housing like the one for Hubble's main mirror would trap heat, so the JWST's mirror is free of an enclosure and measures 6.5 meters or 21.6 feet across. The primary mirror is made up of 18 hexagonal segments that can be precisely rotated along its 7 unique axes to concentrate the picture for optimal clarity and detail. Furthermore, it doesn't orbit the Earth like the Hubble does, where the perpetual cycle of day and night would result in jarring temperature variations on each orbit. Instead, the JWST maintains a station that is 1 million miles away from Earth. The gravitational attractions of the Earth and the Sun balance each other out at this point in a space known as the Lagrange L2 point. So, why does this kind of observation work? Because atoms and molecules have different patterns of wavelengths that they absorb, similar to how people have distinguishable fingerprints and DNA sequences. Then, based on the graph's absorption pattern, locations, heights, and peaks, scientists can identify and quantify the amount of important gases in a planet's atmosphere. WSP-96b spectrum was recorded by Webb's near-infrared imager and slitless spectrograph, or NIRISS, and it not only contains the most accurate near-infrared transmission of an exoplanet atmosphere to date, but it also spans a remarkable variety of wavelengths, including visible red light and a region of the spectrum that has not previously been accessible from other telescopes. Water and other essential chemicals like oxygen, methane, and carbon dioxide, which are not immediately apparent in the WSP-96b spectra, but should be observable in other exoplanets intended for investigation by Webb, are especially sensitive to this portion of the spectrum. The spectrum will allow scientists to quantify the amount of water vapor in the atmosphere, set limits on the abundance of different components like carbon and oxygen, and calculate the depth averaged temperature of the atmosphere. They may use the data to draw conclusions about the planet's general composition, as well as how, when, and where it originated. The best fit model, shown by the blue line on the graph, accounts for the data, the known features of the WSP-96b and its star, as well as the ascribed parameters of the atmosphere. Because of Webb's cutting-edge design, the measurements have an exceptional level of clarity and detail. The JWST's massive, gold-plated mirror captures infrared light effectively. Its sensitive infrared detectors can spot minuscule variations in brightness, and its precise spectrographs disperse light into rainbows of thousands of infrared hues. NIRISS can distinguish between colors with brightness variations of a few hundred parts per million and color differences as small as 1,000th of a micron. This is very exciting because it covers infrared light wavelengths that we have never had access to before. The infrared atmospheres of exoplanets have been studied by other telescopes, but not to this level of specificity, and this is just one sliver of data. Professor Gillian Wright, principal scientist on the telescope's UK-led mid-infrared instrument, agrees. "We've never had access to something this big in space before," she says. To say a telescope will open up new windows on the universe sounds kind of cliched, but with James Webb, it's really true. In addition to Webb's remarkable stability, the placement of it in orbit near Lagrange point 2, about 1 million miles from the Earth's atmosphere's polluting effects, allows for an uninterrupted view and clean data that can be examined very rapidly. The very precise spectrum created by evaluating 280 distinct spectra concurrently throughout the course of the observation gives just a little glimpse of what Webb will be able to do for the study of exoplanets. In the next few years, scientists will employ spectrographs to examine the atmospheres and surfaces of hundreds of exoplanets, ranging in size from tiny, rocky planets to giants that are rich in gas and ice. One observation period, or almost 1/4 of the Webb cycle, is devoted to investigating exoplanets and the constituent parts of them. This NIRISS image illustrates Webb's capability to describe exoplanet atmospheres, particularly those of planets that may be habitable. The majority of science will be spectra. While we often say that a picture is worth 1,000 words, spectra for astronomers are worth 1,000 photographs. According to Antonella N., a James Webb Space Telescope scientist who heads the Office of the European Space Agency at the Space Telescope Scientific Center. Also, Elon Musk, Tesla Inc. and SpaceX CEO, is excited about the potential of NASA's James Webb Telescope. He made this known through a tweet from his verified Twitter handle on July 13, 2022, that came after NASA shared the first full-color images captured by the Infrared Space Telescope. Excited about @NASA Webb potential. The more we learn about these exoplanets, like WASP 96b, the closer we get to finding one that could be habitable for humans. But until then, let's do what we can to take care of the Earth, because it is a very special place in the universe, and so far, it's the only one we have.